You click your mouse, and instantly, something happens. It feels like magic, right? But behind that single click is this entire hidden universe of logic. Today, we're going to build that universe. We're going to start with basically a grain of sand and end up with a powerful computer sitting right in front of you.
So, have you ever really wondered about that? That feeling of magic? It's not an illusion. It's actually the result of an incredibly elegant and logical architecture. Every single thing your computer does, it follows a very specific set of rules. And our goal today is to understand those rules right from the ground up.
All right, so here's the game plan, our blueprint. First, we're going to lay down the digital foundation, the fundamental building blocks. Then, we'll learn the language they speak. After that, we'll meet the brain of the operation. We'll find a place for all its memories, and finally, we'll put the whole thing together. Let's get building. Okay, first things first. We have to start at the very bottom with the digital foundation. I want you to think of this as having a giant, infinite box of Lego bricks. These are the simplest, most fundamental pieces we're going to use to construct everything else. And this right here, this is our most basic Lego brick. It's called a logic gate, and all it is really is a microscopic switch. It makes one super simple decision. Is the power on? That's a 1, or is the power off? That's a 0. That is it. Every single complex thing your computer does, from playing a game to sending an email, is built from billions of these simple yes or no choices.
So how do we actually build something useful with these tiny switches? Well, there's a rule book, a kind of instruction manual called Boolean algebra. It lets us chain these logic gates together to create a circuit that can perform a specific task, like, say, adding two numbers. And just like that, we've gone from a simple on-off switch to a basic calculator.
Okay, awesome. Our circuits can now do some basic stuff. But what are they even processing? What's the information? For that, they need a language. You and I, we think in 10 digits, right? 0 through 9. It's what we've always known. But a computer, with just those simple on or off switches, well, it's only got two options, 0 and 1. This is the binary system, and it is the native language of all digital hardware. It's the alphabet for absolutely everything that happens inside that machine.
And believe it or not, with just those two digits, computers can represent, well, everything. Your name, the numbers in a massive spreadsheet, the millions of colors on your screen, it's all just patterns of zeros and ones translated into this fundamental binary language.
Okay, so we've got our building blocks. We've got our language. Now, we need a boss, the construction foreman, the conductor of the whole orchestra. You know what I'm talking about. The central processing unit, or CPU. The brain.
The CPU just has this constant, relentless rhythm. You can think of it like its heartbeat. It's called the instruction cycle, and it's a simple three-step dance. Fetch, decode, execute. It grabs an instruction from memory, it figures out what that instruction means, and then, boom, it carries it out. Billions and billions of times per second. This is the pulse that brings the entire computer to life.
Now, what's interesting is that not all CPUs think the same way. There are basically two big design philosophies. On one hand, you have RISC processors. Think of them like a race car. They do a few simple things, like add or load, but they do them extremely fast. On the other hand, you have CISC processors. These are more like a multi-tool. They have more complex commands, like multiply these two numbers and store the result over there all in one step. It's a classic trade-off between pure raw speed and complex capability.
So our computer has a brain. That's great. But what good is a brain without memory? It needs somewhere to store all its instructions and all the data it's working with. But here's the catch. Not all memory is created equal. The way engineers solve this is with what we call a memory hierarchy. Just picture a pyramid. Right at the very top, you have the cache. It is super, super fast, but it's tiny. In the middle, you've got your main memory. You probably know it as RAM. That's the computer's main workspace. And at the bottom, the base of the pyramid, is your large but much slower hard drive. The computer is constantly, cleverly juggling data between these levels to give you the maximum possible speed. And to manage all this, computers have this just brilliant trick up their sleeve called virtual memory. It lets the system use a chunk of that slow hard drive space and pretend that it's actually part of its fast main memory. This is exactly how you can have dozens of browser tabs and applications open all at once, even if you don't have a ton of RAM. So what does this mean for you? It means the whole system is constantly trying to guess what you're going to do next, and it keeps that data in the fastest memory it has available.
That's it. That's the reason why your most used apps feel like they open almost instantly. It's the memory hierarchy just working perfectly in the background for you.
Okay, we are so close. We have all the major parts. We've got the logic circuits, we have the brain, and we have the memory. Now for the final, crucial step. We gotta hook everything up so they can all work together as one single harmonious system.
And the key to this connection is something called the bus system. Seriously, just think of it as a network of superhighways running through your computer. It's the physical road that lets the CPU send instructions to your memory and lets your graphics card get the data it needs to draw what you see on the screen. Without the bus, all the parts would just be sitting there, isolated and totally useless.
And finally, the whole system has to talk to the rest of us, right? To the outside world. That's where input and output, or I/O, comes in. This is everything from your keyboard and mouse to your monitor and speakers. And to keep things running fast, the system uses clever tricks like direct memory access, or DMA, which lets your hard drive send data straight to memory without ever having to bother the super busy CPU. It is all about efficiency.
And you know, this architecture is never standing still. It's always evolving. We've moved way beyond computers with just one single brain. Now we have systems with multiprocessors, or more commonly, multicore chips. It's like going from having one person trying to do absolutely everything to having a whole team of experts all working together in parallel. It's the reason why even your phone can handle so many complex things at once.
And there you have it. From one single on or off switch, we've layered on all of this ingenious design, and we've built a modern computer. It is an absolutely incredible testament to human logic. This whole incredible journey started with just one simple switch, which kind of makes you wonder, doesn't it? What's going to be the fundamental building block of the machines of tomorrow?